All right, who's ready to get started? Let's go. I like that attitude. Let's go. We are doing today the second of two topics that I think of as being probably the most central to this course, right? Last time we did nodal analysis, and this time we are doing mesh analysis. And I really liked what someone said one time, and I was trying to remember who said this, but it was one of my friends who, after we learned about mesh analysis, he goes, now we're using KVL to its fullest potential. And I kind of grinned at that because there's a pun in there, right? I don't think he meant to do that, but there's a pun in there, right? Whenever we use Kirkhoffs voltage law, another word for voltage is potential. So anyway, I like to call this lecture, we're going to use KVL to its fullest potential, okay? So let's kind of go through a little bit of review stuff. First of all, we did already cover that there is a special kind of loop that is called a mesh. A mesh is a loop that does not contain any other loops inside of it, okay? And what we're going to do with this topic is we are going to first identify meshes, and then we're going to do some kind of an analysis on the meshes that we identify, okay? So before we really get started with this, let's make sure we understand what we're talking about with meshes. And so I did this really brief here example problem. Where are the meshes in that network that I showed right here? These are little circuit elements that are connected in this little network. Where are my meshes? Okay, so it's hard for you to probably communicate this, but one of them is right here. There's no loop inside of that loop, right? So then there's another loop maybe right here, right? And then a third loop up here, right? These are the mesh loops that are in this circuit. Are there other loops? Okay, there are, but they are not meshes. Now here's the thing, Kirkhoffs voltage law says the sum of the voltages around any loop is 0. It just so happens that in this lecture we're going to identify the specific loops that are meshes and do sums of voltages around those. Okay, so a few, I may not get them all here, but a few of the other loops might be something like this, right? This would technically be a loop. Do you agree with that? You can go all the way around that way, or you could have another loop that goes up around this way. Again, my goal is not to necessarily, be exhaustive in all of my identification of all the loops that we can have there. It's more or less to try to get us to see there's a difference between a mesh as a specific kind of loop and just any old general loop. KVL applies regardless of what kind of loop you are looking at. It just so happens we're going to focus our attention on meshes in this lecture today. Okay. Next, I have to define this thing called a mesh current, right? I'll put this right here. A mesh current is a little bit hard for some people to grasp because it's something that we set up as an abstract idea, okay? The abstract idea of a mesh is to basically say, let's pretend, a mesh current is to say, let's pretend that each of these meshes has a uniform current flowing around the mesh, okay? Now, if you look at any of the conductors that form the mesh, they may not have that current in them, right? But we can sort of identify this as being the overall current that goes around a mesh, right? So, kind of as a corollary of that, anytime you have an element where it is only a part of only one mesh, it just so happens that that mesh current we've identified will be the current going through that element that is only a part of that mesh. Okay, so an example of that, this element over here, right? See that element? How many meshes is it a part of? 1. And so that means when we define a mesh current being like a current that flows around this mesh, the mesh current that we define will be the current that that element experiences. Okay? What about this element up here? Okay? So that's kind of the third little block that I've got right here. If you've got an element that's part of more than one mesh, then the actual current that flows in that element is actually going to be the sum of all the mesh currents flowing through that element, right? So if it's, actually, I tell you what, let me go on and identify this one right here. Let's say that that element right there is this element here, okay? And when we identify the mesh currents, basically the current flowing around one of the meshes and a current flowing around the other mesh, the current that's actually flowing through that circuit element is going to be the algebraic sum of the two mesh currents that join together to put the, the actual current that goes through that element. Does that make sense? Okay. And so that's where I put this little equation down there. The actual current through the element is, the first mesh current minus the second mesh current. Okay? So now let me kind of help to justify for you that this is valid. Right? And we'll do it with a real quick little example here. Let's say that I have that little network that I identified earlier, and let's start applying some mesh currents to it. I'm going to make these mesh currents up, but I'm going to show you that they are compatible with the idea of the Kirkhoffs Current Law, meaning that the sum of all currents flowing into and out of a node has to be 0. It turns out that these meshes and kind of how we're setting up these meshes is compatible with the idea that Kirkhoffs Current Law can't be violated, okay? So here's how we'll do it. Let's say that my mesh current in this mesh, I'm just going to make up numbers here. Let's say that's 9 amps flowing around that, okay? Now the mesh currents don't have to be defined all the same direction either. They can have a mesh current that goes the other. In other words, I did that one clockwise. I can pretend like another one here might be counterclockwise. So let me just, again, I'm making up another value here. It doesn't matter what value I make up right there. What I'm about to show you will hold. Okay? And then let me make up a third value here. Let's say this is around this mesh up here is 1 amp. Okay? Now let's see if we can determine how many amps flow through each one of our circuit elements. Right? Let's do a couple of the easy ones first. How much flows in this circuit element over here? 9 amps. Why? Okay. There's only one mesh that circuit element is a part of. So whatever that mesh current is, that's going to be the current that flows in that circuit element. Okay? Let's move on and do one that's a little bit trickier. What about this circuit element up here? I'll highlight it here real quick. What about that circuit element right there? Okay? There's 9 amps flowing to the right, but then there's what? 1 amp that flows to the left. So the net current that flows through that little circuit element is going to be what? 8 amps to the right. Agreed? Okay, does that kind of make sense? That if we take the combination of the 9 amps and the 1 amp, those would sum to only 8 amps going to the right. Okay? What about this circuit element here? I'll highlight it green. What about that one? Okay, that one's going to be 14 amps down. Okay, how do we know that? Okay, because the 9 amps has its loop kind of pointing generally downward, right? And the 5 amps also has its loop pointing downward. So those two would add together to make 14 amps coming downward. With me so far? What about this circuit element up here? I'll highlight it purple. Okay, kind of like the one we just did. The arrow of the 5 amps comes the same direction as the arrow of the 1 amp, right? At that circuit element. And so that means that this current right here is going to be 6 amps. All right, now here's my question. This is the first one I've been able to do this with. Look at this node up here. Okay, so let's say we're looking at this node right here that I just highlighted in blue right there. All right, is Kirkhoffs current law satisfied for that node? It is, right? And this is for just randomly made up numbers, right? I could put any numbers in here I wanted, 9, 1, 5. It doesn't matter that it was 9, 5, and 1 for these. I can make any numbers up, and we would find that Kirkhoffs current law would be satisfied at each one of the nodes. You want to check the other ones and just make sure? Okay, this one here, we have 5 amps coming up this way, right? What else do we have? 1 amp coming this way, right? And then what else? We already said we have 6 amps flowing this way, so that would also imply we have 6 amps flowing this way on that leg. Is Kirkhoffs current law satisfied at that node? We're good, right? And then what about over here? Here I've got a 1 amp flowing this way and an 8 amp flowing this way. Okay, so this is a property of identifying these meshes and then identifying the mesh currents. It just so happens that doing that allows us to satisfy KCL in kind of a different way. Does that make sense? Okay, and I don't want to beat it too much, but that's, this is sort of the basis. We have to kind of be comfortable and agree that this is the way it will probably work. Now what we need to do is think about using Kirkhoffs voltage law, okay? And what mesh analysis is that you take Kirkhoffs voltage law and you apply it individually to each one of your mesh loops, all right? When you do that, you do it in terms of the currents that flow in each branch of the circuit, right? So if you have a resistor and you define a particular current that's flowing in 2 different meshes, right? Let's say I define a current. Let's say I don't know these currents, right? Instead of knowing it's 9 amps, 5 amps, and 1 amp, let's say those are 3 unknown currents, right? Could I define the voltages of each one of my circuit elements in terms of those currents if they are resistors? Yeah, because I can set up an equation that would give me the current through each one of those resistors, and then I take the current multiplied by the resistance value, that gives me voltage. Okay? It'll make a lot more sense once we get ready to do this problem. So kind of like I did last time, I've listed out the steps of doing one of these mesh analyses, and what we're going to do is kind of follow through these steps on a particular circuit so you can see how this works. Okay? So the first thing to do is to identify your meshes by drawing and labeling your mesh currents. Okay? And you do that essentially with these little loops, right? So I'm going to start down here in the lower left-hand corner and call this current in this loop here I1. Okay? In this case, I have enough information here in this circuit that I could solve for all of my mesh currents. It's just that I don't know what they are right now, so I can't do something nice and easy like just say that it's some value. It will be some value, but I have to determine what that value is, right? So I'm going to assign it a variable and say I'm going to solve for these mesh currents. So there's one of my mesh currents. Let me put another mesh current over here. Okay, I'll call that I2. And then I'll put my third mesh current up on this upper mesh up here. I'll call that I3. Okay, so step 1 was identify the meshes by drawing and labeling the mesh currents. And we just finished with that step. Okay, step 2, write Kirkhoffs voltage law equations around each mesh. And many times when you do this, you'll have to do it in terms of the mesh currents that you just labeled with these variables. Okay? So a lot of times it's helpful to go ahead and label which one you are working with. I'm going to say, let's start with mesh 1. Okay? Mesh 1. What would this look like? And generally, what I do when I do these, not necessarily always, but generally, I take whatever kind of the beginning of that arrow was, and I kind of imagine the circuit elements that this current goes by, and so that way I make it all the way around the loop and I account for everything. So I pick a starting point and I start going around the loop. Okay? So I'm going to pick that as a starting point right there. And what do I have as I start summing these voltages around that loop? The first thing I have is minus 90 volts, right? Easy, right? Minus 90 volts. And then I come up around here, and the next thing where I can have a voltage drop is on this 45 ohm resistor. How much voltage is going to be across this 45 ohm resistor? Okay? It's based on the current flowing through the resistor and the resistance value, right? And so how much current flows through that resistor? I1 minus I3, right? We said that a few minutes ago, that basically the positive direction of voltage for the 45 ohm resistor, if we assume that positive direction of voltage is like I just labeled right there, then that means we're taking rightward current to be positive, right? So that's why I take I1 minus I3, is that to have a voltage positive the direction I just showed it, there better be a net current flowing to the right. All right, as far as my sign, making sure my signs are consistent. Okay, so what I'll do here then is add I1 minus I3. Okay, but that's a current, and I can't just add that to a voltage, right? What do I need to multiply it by? 45 ohms. Ohms times current is going to give you volts, so I can add that to my voltage sum, right? Okay, then where do we go? 30 ohms. Okay, so the voltage I have across my 30 ohms works kind of the same way. If I assume positive voltage coming this way, then I would say I1 minus I2 is the current, and 30 ohms is the resistance. And do I have any other elements where voltage can drop? Or do I just have wire after the 30 ohm resistor around to where I started my loop? Just wire, so that means there's zero voltage assumed on that. So that means, what can I say about this sum that I just did? Okay, it has to satisfy Kirkhoffs voltage law, so it better sum to zero. Okay, now, at this stage, probably a good idea just to think critically about that equation. How many unknowns do I have in that equation? Okay, so I can't solve that equation by itself, can I? All right, just make that comment there. What is the next step? Like, where are we in our steps here? Okay, are we to step 3 yet, or have we finished with step 2? Okay. Yeah, we are not done writing all of our KVL equations for all of our mesh loops, right? So let's kind of finish that part out and finish up with step 2 before we move on to step 3. All right, so what about mesh 2? Okay, again, I'm going to start at the beginning of my little loop arrow right there. What will I have there? Okay. The easiest way to do this in my mind is to always take the current, the mesh current in the mesh you're in, and put it first in the little differences in currents that you a lot of times end up with, right? If you do that, then you'll end up with a positive voltage, right? So if I say here I've got 30 ohms times I2 minus I1, that makes sense, because I'm now assuming the voltage across this 30 ohm resistor is positive with the positive down here. Okay? And this is not inconsistent with the last one I did, because each one of these sums can be done separately. Right? Even though I'm assuming that voltage is opposite in this sum than I did on the last sum, it doesn't matter, because all I have to do is make sure it's consistent with the term that I'm writing in that instance, right? So this term assumes that I2 minus I1, right, gives you a current that flows upward, and that would assume that a voltage was positive on the bottom side and negative on the top side. So I'm consistent internally with what I'm doing in this sum. Okay, what's the next piece? If I kind of keep going around this loop, what's the next circuit element that I come to? 60 volts. And here's the thing, voltage sources are wonderful. Why is that? Yeah, they're easy to deal with. You know what the voltage drop is on a voltage source. Doesn't take any thought whatsoever. Okay? So we come to the positive terminal first, so we just add 60 volts. Okay? Then what? Okay. So then what we come to is 75 ohms, and you'll notice there that for the 75 ohm resistor, its current through it is only I2, right? Because there's only one mesh that resistor is a part of. So I'm going to add 75 ohms times I2, right? And that gets me all the way around that mesh loop. So that's something I can set equal to 0. All right, I'm going to say the same thing here. At this point, the combination of these first two equations, are they solvable? Okay, still not. Why not? There are 3 unknowns and only 2 equations, so we're still not ready to solve this thing. So that means we should probably move on to our next mesh. Okay, mesh 3 is up here on the top. What's our first circuit element we come to if I start again at the beginning of my little loop there? What's the first circuit element I come to? 15 ohm, and assuming this is the direction of positive current, I'm going to have positive 15 ohms, okay, times I3 as the voltage across the 15 ohm resistor. Okay, I'll keep coming around the loop now, and what's the next thing I come to? The 60 volt source, but now I come to the negative sign of the 60 volt, the negative terminal of the 60 volt source first. So how do I count it in my loop? Okay, negative, we'll count it as a minus 60 volts, right? Then what? Okay, now if I assume I3 minus I1 is the current across my 45 ohm resistor there, then what I'm going to have is 45 ohms times I3 minus I1. Okay, and does that get me all the way around the loop? Looks to me like it does. Okay, now we've done our third mesh, and we are very hopeful now that we end up with something that's solvable. Is it solvable? It is, right? Because now we have 3 independent equations. They are all independent because they came from different principles, right? Sum of voltages around one loop. Separate principle is the sum of voltages around the other loop has to be 0. Third principle is the third loop. That sum of voltages has to be equal to 0 as well. So these are 3 independent equations, and they have 3 variables in them. It's likely that they are solvable. Okay, shall we solve them? Of course we should solve them. Okay, tell you what I'm going to do real quick is I'm going to rewrite each of these equations to make it convenient for calculator entry. Okay, how do we do that? All right, for the first one, I'm going to look for everywhere I have an I1, right? And what I find is that I've got a 45 ohm and a 30 ohm You know, those are two coefficients multiplied by I1. So I'm going to take down here and say 45 ohms plus 30 ohms, I1, then what? Okay, plus 30 ohms, I2. Okay, excuse me, good catch. I said plus. Is it plus? No, there's a minus sign right there, so thank you for catching me on that. Okay, then what? Okay, minus 45 ohms times what? I3. All this is equal to, okay, 90 volts. Okay, so there is that's a nice format for how to enter this into a calculator if you're going to try to use a calculator to solve this system. Let's do the next one. I'll go just a little bit quicker. Here I'm going to have a minus 30 ohms, I1. Then I will have 30 ohms plus 75 ohms, I2. Then I'm going to, do I have any I3s? Okay, so sometimes I do this. I won't necessarily always do it, but a lot of times I'll do something like this to really emphasize there is no I3, so I just use a coefficient of 0 for I3. Okay, then what? Okay, this should be equal to negative 60 volts. Okay, make a little squiggle right here so that we can keep separate what we're doing. All right, the last one, I'm going to have negative 45 ohms, I1. Okay, do I have any I2s? Okay, I do not. So I'm going to say plus 0 I2. All right, plus, and then I have my last one is going to be 15 plus 45. 15 ohms plus 45 ohms. I3. This will be equal to what? 60 volts. Okay? And so now what we have are all these coefficients, right? Got a coefficient here, here, and here, 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 and here. Plus we have all these constant terms on the other side. Those are the bits of information we have to enter into most calculators out there in order to be able to solve for all of the things that we're trying to find. Okay, so let me get in here and do equation mode. My 3x3 is option 2 in this calculator, and I'm going to enter these. 45 plus 30. I've got negative 30 for my next one. I've got negative 45 for the next one, and then 90 for the last one in that equation. Here I've got negative 30. Here I've got 30 plus 75. Here I've got 0. And then lastly I've got negative 60. Okay. The last equation I've got negative 45, 0, 15 plus 45, and then 60. Okay, when I hit equals, I come up with answers. Okay, so this is the solution I'm about to write down right here. My first mesh current, I1, is going to be 3.607, let's say. Okay. I1 is equal to 3.607 amps. Okay. What's I2? Okay. 0.459. And then lastly, 3.705. Okay, so what we just finished with is step 3, right? We're going to solve the resulting system of equations to find mesh currents. We just did that. We got all of our mesh currents here. Now I added a step 4 here so that you understand that it's not uncommon for us to need to know something that may not be directly given with my mesh currents, right? So it says if you need to know I, or V for that matter, for an element that is part of 2 meshes, right, then the mesh currents themselves, those numbers aren't going to immediately give you the current through those elements. But they give you really easy tools to get there, though, right? For instance, what if I need to know the current through the 45 ohm resistor? I'll label it I 45 ohms, and let's, just to be clear on this, let's say I'm taking I 45 ohms to be this way. Okay, this is going to be equal to I1 minus I3. And since I have those over here, this is going to be equal to 3.607 amps minus 3.705 amps. And so what is this going to be? Okay, this is the current through my 45 ohm resistor. What does the negative sign mean? Yeah, whatever direction I assumed that it was positive when I drew it up there, it's really the opposite direction of that. So it doesn't flow from left to right, it flows from right to left. That's what the negative sign means. What if I wanted the current through the 30 ohm resistor? Okay, first of all, define what direction you're taking to be positive. I'll just show it this way. Let's say this is I of the 30 ohm. That'll let you know which direction to do your sum. Then what? This will be I1 minus I2. Okay, what's that? 3.607 amps minus 0.459 amps. And so what is this? Okay, positive, right? What does that mean? Okay, that means the arrow I showed, that really is the direction that the current flows. Okay, we could do other ones as well. You know, for instance, what if I needed to know the current through the 75 ohm resistor? Yeah, 75 ohm resistor gets a current of I2, right? I2 is what goes through the 75 ohm resistor. So there's no like post-processing that I need to do for that one because it's only part of one mesh. What about the 15 ohm? Same deal, right? It gets a current here of I3. So there's, again, no post-processing I've got to do to figure out that current. What if I need to know the voltages across all my resistors? Ohm's law, right? Now we know all the currents across all the resistors. All you have to do is take that net current across each resistor and multiply it by that resistance value for that resistor, and that gives you the voltage across that resistor. Okay? What if I need to know power? You can do I squared R, okay? Or if you happen to know the voltage, you can do VI, right? So anyway, there's a lot of different things you can do. Finding those currents, though, those mesh currents, is the key step along the way to get the thing that sometimes you really need. Okay? Any questions before we move to the next example? Yeah? Okay, his question is, let's say you're doing an example where you don't have a voltage source somewhere in it to kind of tell you a direction that voltage is going. That's your question? The thing is that defining the direction of your mesh currents is arbitrary. You get to decide how to do that. Now, my recommendation is pick one direction and keep it that way for all your meshes. What benefit do you get from doing that? Okay. The format of how you write your equations will end up very consistent. If you choose clockwise, let's say, it doesn't have to be clockwise, you can do counterclockwise if you want, but once you pick it for one of your meshes, I would use the same direction of current assumed for all your meshes. Again, that's a choice. You get to do it however you want, but if you choose different directions for your mesh currents, then sometimes you're going to end up with differences of currents, and sometimes you'll end up with sums of currents when you do your individual terms in your loop equations. I find it easier to not make mistakes, let's say it this way, if you choose one current direction and keep that same current direction assumed for all of your mesh currents. Does that make sense? So that's how I'm going to do all my examples here, but it's a good idea to emphasize that is arbitrary. You can decide to flip the direction of your mesh currents, and the only thing that means is that when you finally solve for them, your positives and negatives are going to be with respect to whatever you had them assumed as. Does that make sense? Okay, good question. Other questions before we move to the next example? Yeah.
Does this also work with dependent sources?
Okay, you're going to have to wait not one example, but two examples to get to that question. The question was, does this work with dependent sources? And the answer is, yes, it does. So, but I will wait for just a minute here to get to that question. Ready for the next example? All right. The next example, the big heading on it is, what we just had was voltage source, or two voltage sources in that last example. What happens if we have current sources? Okay? This presents a challenge to us because current sources don't make any implication about what voltage is across a current source, right? You can't just look at the current source and see the current that's flowing and automatically know what voltage that current source is going to have across it. Okay? How much voltage is across a current source is a function of the rest of the network, right? It is actually going to be set by what happens in the rest of the network. So we can't locally look at one piece and say, I know how much voltage is across it. Okay? By the way, what we're trying to find in this little example is we're trying to figure out the power that's supplied by the 2.2 amp source. All right? Now, I had a teacher when I was in high school, and he always made this thing. His name was Mr. Godfrey. Mr. Godfrey would say, what do you do when you don't know what to do? And he had an answer for that question. Okay? He would say, you do what you know is not wrong. That doesn't necessarily mean it's going to be the thing that gets you to the end that you want, but if you don't know what to do, doing something that you know is not wrong at least gets you some new place where you might figure out the next right thing to do. Does that make sense? So that's kind of the nature of this question in orange that I have over here. What do you do if you don't know what to do with a question like this? The essential problem is that we don't know the voltages across the current sources. So what should we do? Okay, I have it written up there. Declare variables for the current source voltages, because the essential problem is we don't know what those voltages are. So let's just say, well, okay, we don't know what they are. Let's make a variable to describe them, right? I'm going to do that such that I assume they are going to be producing positive power. Okay, I'm going to call this one V1. I've got another current source here as well, right? The 3 amp source. what direction would the voltage go if I'm assuming the 3 amp source produces positive power? To the left, right? I'll call that V2. Does this mean that I know that they are producing positive power? No. All it is I'm choosing a direction. It is somewhat arbitrary. I'm just stating at the beginning, if it turns out that the V1 and the V2 are positive, it means those sources are delivering power into the network, right? They are supplying power into the network, not absorbing power if those numbers come out positive for V1 and V2. Okay? All right. How does that help me? Or it may not. Let's see if it does. Okay? Let's start thinking through, now that I've applied those two unknowns, V1 and V2 in the circuit, what were the normal steps that I had to go through for my mesh analysis technique? First one was, okay, let's identify the meshes by drawing on their mesh currents. Okay? So I'm just going to start at the upper left-hand corner, and let's say that up here, I'm going to define this mesh current starting here, and we're going to call that I1, just like I did last time. I'm going to go across to this next one here, right? Let's say this is my next mesh current. Okay, I'll call that I2. Let me go down here next and define a mesh current right here. I'll call this I3. Excuse me, I'm trying to stay consistent with the kind of the notes that I have here, and I just realized that in my notes, I think I labeled them this way, so I'm going to relabel those. I1, I2, I3. Here we'll call this one I4. Okay, and this, I try to be somewhat clear about where I'm starting and ending. So I'll call that I4, and then for the last one over here, I'll call this I5. Okay? So that was step one, was to basically identify your meshes by drawing your mesh currents and labeling them. Okay? What's next? Okay? Yeah, I'm going to put a big heading right here to say, let's do our mesh loop KVL equations. Okay? And we'll start with mesh 1. Okay? If we start at the beginning, like kind of this point in mesh 1, what's the first circuit element we hit? The 21 ohm. And so what we would have there would be 21 ohms times what? I1, right? There's no other meshes involved on the 21 ohm resistor, and so it's just the one current that we have to think about there. Okay, what's next? Plus 26 ohms times what? Okay, I1 minus I3. Okay, then what? Okay, because I didn't know the voltage across my current source, I just defined that variable. So what do I do here? Okay, not minus, I'm coming into the plus sign, right? So that means I say plus V1. Does that get me all the way around that loop? Yep. Okay, let's get through the other ones here. Mesh 2, right? There, I'm going to have minus V1, right? Plus 23 ohms times I2 minus I4. Okay? Plus 27 ohms times what? Okay? That one, how many currents are involved? Just one current, and it is I2. Okay? Did that get me all the way around the loop? Okay, so I'm going to set that equal to 0. All right, what's next? Mesh 3, we'll just keep on working on all these. For mesh 3, I'm going to have I3 minus I1 times 26 ohms. I'll do the 26 ohms first here. I3 minus I1. Okay. Then I go up to the 24 ohm. What currents are involved in the 24 ohm resistor up here? Okay. Just I3. So I have 24 ohms, I3. Okay. Then I hit this voltage source. What do I do with that? Easy, right? All I got to do is say plus 25 volts. Okay. Then I come around and I hit this 31 ohm resistor. Okay. It's going to be based on which currents? The voltage is going to be based on, okay, 31 ohms times I3 minus I4. Does that get me all the way around that loop? It does. We go to mesh 4. Okay. For mesh 4, I'll start going across the 23 ohm, right? So the 23 ohms times I4 minus I2. Okay. Then what? Plus 31 ohms. Okay. You say I4 minus I3. Right? Then we come to 29 ohms times I4 minus I5. And then what? Minus V2. And then does that get me all the way around the loop? Only one more mesh left to go. Okay, we'll go to mesh 5 here. All right. So mesh 5, we'll start at the 29 ohm. All right. The current through there is going to be I5 minus I4. Okay. Minus 25 volts would be the next element, plus 28 ohms times what? Okay, just I5, because there's no other meshes involved on that resistor, the 28 ohm resistor. Okay, and that gets me all the way around the loop, right? So we'll set this equal to 0. Now, a quick inventory, right? How many unknowns do I have total? Okay, I had the 5 mesh currents plus V1 and V2. Okay, how many equations do I have? Okay, 7 equations, 7 unknowns, 5 equations. Right? Is that a problem? Okay, initially it is. What do we do about it? Okay, I'm going to put over here, these were the mesh loop KVL equations. Let's have a couple of extra equations over here. Okay, one of the extra equations is the 2.2 amps that I have for this current source. That information hasn't come in yet, right? But I can add it, right? Because it's telling you the current on that little leg is 2.2 amps, but we have a way of defining that current in terms of our mesh currents, right? So I would say it looks like I2 minus I1 is equal to 2.2 amps. Do you agree with that? So there's a 6th equation now, right? Can we do something similar for the other current source? Yeah, it's actually even better. we know I4 already, actually, right? Because I4, that mesh current, where it goes through this current source right here, that is the only current that's involved. That's the only mesh current that's involved with that current source. So that means that I4 is simply equal to 3 amps. Okay? So that's an easy substitution to do, right? To get rid of one of our unknowns being I4, you can substitute 3 amps in anywhere there's an I4. Does that make sense? So that's nice. And that means that we're at, depending on how you look at that last equation we just wrote, we're either at 6 equations, 6 unknowns, or we're at 7 equations with 7 unknowns, right? Depending on whether you decide to do that substitution formally or not. All right? Does that mean we're in good shape? Yeah, we should be able to solve that, right? Is that something that you would like to have to do when you are in the middle of an exam, let's say? Okay, in the middle of an exam, many of you will have calculators that will do up to a 3x3. Some of you might have one that'll do a 4x4, but you would actually really like for this to actually be a smaller system. Would you agree with that? What if I show you a way to make that happen? Okay. When we looked at the nodal analysis question, we had supernodes. Would you like to come up with something we call super meshes? Okay. Ask and you will receive. So you start the process the exact same way that we did the last one. You still want to define mesh currents for all of your actual meshes. So that's why I left everything that we already had defined on the figure, right? Still, we're going to start it the exact same way. But what we're going to do now is look at anywhere you have a current source and you decide, I am not going to do individual meshes across that current source. I'm going to pretend like I can skip right over that current source. Here's what that would look like in this left set of meshes over here, right? What I can do is I can say, instead of going around and like cutting over through this current source, I'm going to make this mesh go all the way up here and all the way back down, right? Now, I'm not going to define any other currents, right? When I show that mesh that I show right there, I'm doing it for the purpose of showing you the path along which we are going to sum voltages. But I'm going to leave it in terms of currents I1 and I2. Okay, we good with that idea? That is what's called a super mesh. All right. Now, how does this change things? Okay, let me write the voltage loop equation for this super mesh, right? So we're going to, again, start down here. Actually, the first circuit element we come to is what? Okay, 21 ohms. Tell you what, I want to label this too so that it lines up good in your notes and everything. So let's say we're doing our super mesh loop equation right here. So we end up with a 21 ohm times what? Simply I1, right? Then what? Okay, plus 26 ohm. Here we've got I1 minus I3. Then what? Plus 23 ohms times, okay, I2 minus I4. What's I4? Why don't I go ahead and do that substitution? Does that sound good? All right? Now, does that get me, oh no, I've got one more piece, right? What do I do next? Okay, plus 27 ohms times what? I2. Okay, before I go too much further, let me show you something. Look at equations for mesh 1 and 2 the first way I did this. What did we essentially do with our supermesh? I basically combined across this V1, right? Imagine solving one of these equations for V1 and then subbing it into the other one. The equation I came up with is exactly that. Of course, I subbed in my 3 amps for my I4 as well. But that's exactly what doing that supermesh did for me, right? And it makes it to where I didn't have to define that V1 value, right? I didn't have to use that technique of defining these unknown voltages across my current sources. Okay, so that's handy. What about all my other meshes? Okay, that actually essentially took care of meshes 1 and 2. Does anything change with meshes 3, 4, and 5? Okay, I would say the only thing that really changes is we could sub in the value for I4, just like I did on this first one. So I'll tell you what, I'm going to grab all these and copy them, because nothing really changes for all of these. All right, let's see. Copy there. I'll paste this down here, and I'll kind of fix everywhere where I have an I4. I'll take and put 3 amps. Okay, I4 right here is 3 amps. I4 right here is 3 amps. Okay. Did that get me all my I4s? I think so. Okay, now let's take stock again. How many equations, how many unknowns that I have written right here? Right now, I've got 4 equations written in, okay, I've got I1, I2, I3, I5, and V2. So I've got 5 unknowns and 4 equations. Is there anything I can do about that? Okay. I have my extra equation, right? What's my extra equation? Okay. I2 minus I1 is equal to 2.2 amps. Okay. Now, is that solvable? That's solvable, but now it's a 5 by 5, right? Are you happy on an exam yet? Let me show you some really neat tricks you can do here. What equation or equations does V2 exist in? Mesh 4, right? What if I pretend I don't have that equation? Now, I might be able to use it later. I don't need to throw it away entirely. There might be some use for it. But what if, in the process of solving this sucker, I pretend like that's not something I need or want? What does that do? It eliminates one of my unknowns, because it's the only place that V2 showed up. So now what do I have? I had a 5 by 5. Removing that equation gives me a 4 by 4, right? Are we happy about that? Okay. Let me do another one that might make you happy. How many unknowns are in mesh 5? How many? 1. You don't even need a system for that one. Say solve directly for I5. Right? Now let me ask you this. Does I5 show up in my Supermesh and Mesh 3? Anywhere? So that equation, essentially all by itself, you can find that I5 might be of interest to you, but you didn't need it to be a part of the rest of the system to find it. So essentially, if I eliminate that equation from the overall system, what does that reduce me to? 3 equations, 3 unknowns, right? The 3 unknowns are I1, I2, and I3, right? The 3 equations are the supermesh, mesh 3, and the extra equation, right? And so you can enter those equations into your calculator and come up with answers very quickly. All right, so we just, by some fairly simple logic, we just reduced this thing from a 7 by 7 down to a 3 by 3. You like that? Okay. So here's what I'm going to do, because, you know, watching me punch values into a calculator is only of limited value, I think. And so what I'm going to show you is how these equations could be rearranged to put in the calculator. Just so happens I have those right over here. Okay. If you put in those equations into the calculator, you will get I1, I2, and I3. Okay. I also listed in this little solution box over there I5. Where did I get that from? I just solved that one equation that I identified up there for I5. Okay? So I'll tell you what, let me grab this. I'll move it into my screen, because we might want to use some of these results in our future calculations. Because what were we supposed to find? Set up here, find the power supplied by the 2.2 amp source. Okay? What do I need to know to find that power? Okay? It would be real nice if I knew V1, right? If I knew V1, I can also say at the beginning I assumed it was supplying positive power, right? So if I come up with a number for V1 and multiply it by 2.2 amps, what does that give me? That gives me the power that's being supplied. Okay? How do I find V1? Okay? I need to pick a loop somewhere. The one that seems to me like it makes sense to use is loop 2. Right? Because if I do loop 2 and I sum voltages around that loop, what I have is minus V1. So maybe I'll put a heading on here. Summing voltages around loop 2. Okay. When I do that, I will have minus V1. Then what? Plus I2 minus 3 amps. And what's I2? Okay. 1.9837 amps minus 3 amps, right? That's the current flowing through that 23 ohm resistor. So I'm going to multiply it by 23 ohms. Okay. Then what other circuit component do I come to around that loop? The 27 ohm resistor. And what current flows through that? Yeah, I2, which is going to be 1.9837 amps. This had better equal 0, or else KVL won't be satisfied. Okay? So then you just solve this thing for V1. When you do that, V1 will turn out to be, let's see, I've got it up here somewhere, 30.185 volts. Okay, is that what I was looking for? Not quite yet, but I'm almost there, right? What power is supplied by the 2.2 amp source? It'll be that 30.185 volts multiplied by 2.2 amps. And again, because that's how I set up my voltage direction to begin with, was to assume that it was delivering power, supplying power, right? I just take these numbers directly. I wound up with a positive number for V1, which means it confirms the direction I assumed that voltage was, which confirms that I'm supplying power, not absorbing it, right? And so this is a positive 64, where is it? 66.4, excuse me, watts. And that's the answer. So how do you like super meshes? They're okay. Don't want to commit, but yeah, they're okay. They're fine. Want to do one more example with dependent sources? I knew you wanted to. All right. On this one, the instruction that is given is to find all of the mesh currents. Okay? Let's go ahead and start defining our mesh currents on the figure. Again, I'm going to start on the upper left-hand corner. You know, I don't have to do that, but let's just say I do that. Start on the upper left-hand corner, define one mesh current right here. I'll do another one right here and call that I2. I'll do another mesh current here and call that I3. Okay, and then my last mesh current I'll put over here, and I'll call that I4. All right, so I just finished step 1 of my mesh analysis technique. Okay. Now, before I go to step 2, would it be handy for me to try to figure out if I've got any super meshes? Okay. A super mesh can be put anywhere you've got a current source, whether it's independent or dependent. Okay. And what it allows you to do is essentially cut the corner, or kind of cut off a spot where you ordinarily would have had to find 2 different meshes. You basically combine those together into one mesh, right? So I'm going to say, it looks to me like we have a mesh where I would have kind of come up along here. Ordinarily, I would have gone through this leg where the current source is, but it's a current source, so I just keep going. I come up through here. Do I go down this spot where I've got this other current source? Nope, I just keep going. Then what? Come down through here. What about my voltage source here? There's no rule about that, so I just keep going. And I come back down through here. This voltage source doesn't mess me up either. So what I just drew right there, that is, if you want to call it a super duper mesh, you can, right? But this is a super mesh. Okay? And then so once I do that, essentially I treat this as if it's only got 2 meshes, right? So that is kind of a step 1A, right? Like a second part of step 1 is to identify any super meshes. Then we can write KVL equations around each of our meshes or super meshes. So that's kind of our next step. So I'll put a heading right here, mesh equations. Okay, and here I'll do mesh, I'll label it super mesh. We'll start with that one. Okay, so there I've got 5 ohms times I3 plus 21 ohms times what? I1. Okay. Then what? Plus 3 ohms times I2. All right. Then what? Plus 1 volt. Okay. Plus Vx over 8. Does that take me back to the beginning of my voltage loop? It does. Okay? So that's the super mesh, and then the other one I will identify here. I'll call it mesh 4. Okay? There I'm going to have minus Vx over 8. Minus 1 volt, okay, plus I4 times 2 ohms. Does that get me all the way around that loop? All right. Now at this point, let's take stock. How many unknowns do I have? 5 unknowns. I've got my 4 mesh currents plus Vx, okay, with 2 equations. So right now we're not doing real well in our count, right? But we have some things that we can start bringing to bear on this problem, right? Like what? Okay, so we'll start with our extras. Okay, one of those extras is that, well, first of all, is there some kind of a relationship for Vx? Okay. Vx is the voltage across the 3 ohm resistor, right? Okay. Yeah, here I called that 3 ohms times I2. But that is Vx, right? Kind of. What's the only difference? Yeah, I2 is assumed to flow from top to bottom, right? And that would make this voltage positive on top and negative on the bottom if that's what it was. So in order to make this extra equation true, what we want to do is say that Vx is going to be equal to minus 3 ohms times I2. Okay. What other extra equations do we have? Okay, so I3 minus I1 is 1 amp. Okay, I like that. What else? Okay, I think I heard someone say I1 minus I2 is what? IX over 13? Okay. How many unknowns do I have now? 6 unknowns. How many equations? 5. What else do we need? Okay. That's an easy one, right? But don't forget about it. It turns out that I4 flows through this 2 ohm resistor, and it's only got that one mesh that it's a part of. So I4 is going to be equal to IX. Yeah, you could do a substitution fairly easily. This is a suggestion I think that was put out just now. Okay, so this might be what you're saying, is that this could be set equal to I4 over 13. And that gets rid of my IX. I think that was the only place we had IX, right? Okay. A lot of times what we're trying to do is get this down to some, a smaller equation or smaller system. What are some ways we can do that? Would it be valid for me to go in and substitute in everywhere I have a Vx and substitute in minus 3 ohms I2? I can do that there, and I can do that right here, minus 3 ohms I2. What does that functionally do now with Vx? I've removed it from my required solution space, right? So that's one thing I can do. So that's good. Now let's think about this. So I've got I3, I1, and I2 in this first equation. I've got I2 and I4 in this second equation. Okay. Is there something else I could remove to try to help myself out? There's a couple ways I can approach this, but this equation right here is relatively easy for me to deal with. It says that I3 is equal to I1 plus 1 amp. Do you agree with that? If I write it in that form, it allows me to go up here and say, where I have I3, let me replace that with I1 plus 1 amp. Let me number these equations. Let's say this is equation 1, this is equation 2, and this down here is equation 3. Between those 3 equations, how many unknowns? I1, I2, and I4. I just created a 3x3 system, right? A couple of easy substitutions. Now I've got a 3x3 system. So now what? Rock and roll, right? Actually, I have this set up again for you so that you can see what this would look like once you enter it into your calculator. All right, let me slide it over here. And that way it looks like it's part of the notes. All right, and then you take that solution of that 3x3, you get I1, I2, and I4. Finding I3 is just a matter of adding 1 amp to I1, right? So that's easy to get I3 as well. What were we supposed to find? all of my mesh currents? Have I accomplished what I was supposed to do? We're good. Okay. All right, any questions about the mesh analysis technique? All right, fantastic.